Morning children, I am E.V. Sasikala, KGBV family from Kannur district. In previous class, we learnt about rational numbers and we solved some problems related to them. Now we are going to solve the problems in exercise 1.3. Before going to solve the problems in exercise 1.3, we have to recall this theorem. Let x is equals to p by q be a rational number such that the prime factorization of q is of the form 2 to the power of n into 5 to the power of m, where n and m are non-negative integers. Then x has a decimal expression which terminates. That means if you take a rational number, x is equals to 3 by 8. If you take a rational number, x is equals to 3 by 8. So, what is they given? Prime factorization of q is of the form 2 to the power of n into 5 to the power of m. For that, we can write prime factorization of 8. 2 4s 8. 2 2s 4, 2 1s 2. Okay, so prime factorization of 8 is equals to 2 cube. Okay, so x is equals to 3 by 2 cube. We can write here 3 by 2 cube. Here, if there is no 5, we can write it as 5 to the power of 0. Any to the power of 0 is 1. Okay, so this is terminates. This decimal form of this rational number is terminates. Why? Because this is in the form of 2 to the power of n into 5 to the power of m. We will take another example. If you take another example, 21 by 5. 21 by 5. 21 by 5. Okay, if you write the prime factorization of 5 ones 5. 5 is prime number. Okay, that's why this number only divisible by 5. Okay, that is equals to 21 by 5. Okay, if you observe the prime factorization of denominator is in the form of 5 to the power of m into this can be written as 2 to the power of 0. Any to the power of 0 is 1. Okay, the prime factorization of denominator is in the form of 2 to the power of n into 5 to the power of m. So this terminates. This 21 by 5 terminates. That means if you take any rational number, prime factorization of denominator can be expressed as a product of 2 and 5. Then that rational number terminates. If we can't write the denominator in the form of 2 to the power of m n into 5 to the power of m, so that is not terminates. Okay, this is our theorem. Okay, did you understand? Exercise 1.3. Write the following in the decimal form and also state which are terminating and which have non-terminating repeating decimal. So here they given some problems. You have to find which are terminating, which are non-terminating and repeating. So if you observe this one, we have to divide 3 by 8. So this is called dividend, this is divisor. If you observe this dividend, 3 is smaller than 8. We can't divide 3 by 8. That's why we have to keep decimal point and we can keep 0 here. We have to recall table. 8 1s 8, 8 2 16, 8 3s 24. 8 3s 24. Okay, 10 minus 4, 6. So, if you observe this one, 6 is also less than 8. We can't divide 6 by 8. That's why we have to keep 0. Again, you have to recall the table. 8 1s 8 like that. You can recall 8 7s 56. 10 minus 4, 6, 4. 5 minus 5, 0. So, again you have to observe this 4. 4 is less than 8. So, we can't divide. That's why you have to keep 0. Already we kept here decimal point. Again you have to recall 8 1s 8, 8 2 16, 8 3 24 like that. 8 5s 40. 8 5s 40. Here denominator here remainder is 0. What is terminating? If we divide a number with another number. If you get remainder is 0, then that is terminating. Otherwise, that is non-terminating. Here we got remainder is 0. That's why this is terminating. Terminating decimal. Terminating decimal. So, if you observe second one, 229 by 400. 229 by 400, second problem. Here also you have to divide 229 by 400. So, if you observe this dividend, 229 is less than 400. So, we can't divide. That's why we have to keep decimal point and we can keep 0 here. After that, you have to recall the table. Okay, 4 ones 4, 4 twos 10, 8 like that. 4 fives 20. 4 fives 20 means 400 fives 2000. So 0 minus 0, 0, 9 minus 0, 9, 2 minus 0, 2, 2 minus 2, 0. Again you have to observe this one. 290 is less than 400. So we can't divide. That's why we have to keep 0. Already we kept a decimal point here. That's why we can keep 0 here. Okay. Again you have to recall. 4 ones 4 like that. 4 sevens 28. 4 sevens 28. 0 minus 0, 0, 0 minus 0, 0, 9 minus 8, 1, 100. 100 is less than 400. That's why we can't divide. Again you have to keep 0. Again you have to recall table. 4 ones 4, 4 twos 8. So 400 twos 800. Again you have to subtract 0 minus 0, 0, 0 minus 0, 0. 0 minus. So 10 minus 8, 2. Again you have to observe this one. 200 is less than 400. Okay. We can't divide. That's why you can keep another 0. Already we kept a decimal point. That's why. Okay. 4 fives 20. So 400 fives 2000. Here we got remainder 0. That's why this is terminating decimal. That's why this is terminating decimal. So, if you divide a number with another number, if you get 0 as remainder, then that is terminating decimal. Okay, next we will go for next problem. 4 1 by 4. This is in the mixed form, mixed fraction form. 4 5 20. 20 plus 1, 21. 21 by 5. Here you have to divide the 21 by 5. Okay, 5. So, if you observe this dividend is bigger than 5. So, we can divide directly. No need to keep decimal point. 5 fours 20. So, 1 minus 0, 1. Again, you have to observe 1 and 5. 1 is less than 5. So, if 1 is less than 5, we can't divide. That's why we have to keep decimal point and keep 0. Again, you have to recall table. 5 ones 5, 5 twos 10. Okay, 5 twos 10. Okay, 10 minus 10, 0. So, here also we got remainder is 0. That's why this is also a terminating decimal. This is also a terminating decimal. Go for next problem. 2 by 11. 2 by 11. So, here you have to divide 2 by 11. If you observe this one, 2 is less than 11. 2 is less than 11. That's why we can't divide. Okay, we have to keep the decimal point and we have to keep 0. Okay, later you have to recall the table. 11 ones 11, 11 twos 22. 22 is bigger than 20. That's why we have to keep here 11 ones 11. Okay, 10 minus 1, 9. 1 minus 1, 0. So, if you observe here, 9 is less than 11. 9 is less than 11. We can't divide 9. That's why we have to keep 0. Already we kept here decimal point. That's why we can keep 0. Okay, again you have to recall table. 11 ones 11, 11 twos 22 like that. 11 eights 88, 11 nines 99. 99 is bigger than 90. That's why we have to keep here 11 eights only. 11 eights 88. Again you have to subtract 10 minus 8 2. 8 minus 8 0. Again you observe here 2 is less than 11. So you have to keep 0. Again, you have to recall table. 11 ones 11. Okay. So 10 minus 1 9. Okay. Again, if you observe this and this, 9 is less than 11. That's why we can't divide. Okay. You have to keep 0. Again, you have to recall table. 11 8s 88. Okay. Subtract. 0 minus 0. 10 minus 8 2. 8 minus 8 0. Again, if you observe this, 2 also less than 11. That's why you have to keep 0. Again, recall table. Again, you have to keep 11. 10 minus 1, 9. 1 minus 1, 0. Again, we can't divide 9 by 11. That's why you have to keep 0. Again, you have to recall table. 11 8s 88. Okay, what we get here? 2. Okay, if you observe this one, we can't get 0 as remainder. And if you observe this quotient 0.1818 like that, this is repeating. That's why this is non-terminating repeating decimal. Non-terminating repeating decimal. So, therefore, here 2 by 11 is equals to 0.1 by 8, 18 like that. This is repeating. This is repeating. This is repeating. That's why this decimal is non-terminating repeating decimal. This can be written as 0.18 bar. 18 bar means these two digits are repeating. That's why we kept here. This is we called this is a non-terminating repeating decimal. Second problem. Without performing division, state whether the following rational numbers will have a terminating decimal form or non-terminating repeating decimal form. Without doing division, we have to find whether the given rational number is terminating or non-terminating. We have one theorem. If the prime factorization of denominator can be expressed as product of 2 and 5, that is 2 to the power of n into 5 to the power of m, then that rational number is terminating. If the prime factorization of denominator cannot be expressed as in the form of 2 to the power of n into 5 to the power of m, that is non-terminating repeating decimal. So, before going to do this problem, first of all, you have to write the prime factorization of 3125. So, this number is divisible by 5. So, at the last digit there exists 5. So, this one is exactly divisible by 5. 5 6 is 30, 5 2 is 10, 5 5 is 25, 5 1 is 5, 5 2 is 10, 5 5 is 25, 5 2 is 10, 5 5 is 25. Okay, 5 5 is 25, 5 1 is 5. Prime factorization of 3125 is equals to 5 into 5 into 5 into 5 into 5. So, 5 to the power of 5. So, 13 by 3125 we can written as 5 to the power of 5. If you observe denominator of this rational number is 5 to the power of m form. So, if the denominator of rational number is in the form of 2 to the power of m into 5 to the power of m or 2 to the power of n or 5 to the power of m, then that is terminating. That's why this is terminating. This is terminating. Okay, go for next problem. 11 by 12. Here also you have to write the prime factorization of 12. 12. 2 6s 12. 2 3s 6. 3 1s 3. So, prime factorization of 12 is equals to 2 into 2 into 3. This can be written as 2 square into 3. So, this is equals to 11 by 12. Okay, 11 by 12 is equals to 11 by 2 square into 3. If you observe, denominator of this rational number is not in the form of 2 to the power of n into 5 to the power of m. There exists 3. That's why this is non-terminating. This is non-terminating repeating. Next, go for third problem. Here also we have to write the prime factorization of 455. 455. This is exactly divisible by 5. 5 nines 45. 5 ones 5. Okay. 91. 91 is not divisible by 3. 5. This is divisible by 3. 7. 7 ones 7. 7 threes 21. 13 is prime number. 13 is not divisible by any number other than 13. So this number is divisible by 13. Okay. Here 64 by 455. 64 by 455 can be written as 5 into 7 into 13. Prime factorization of 455 is 5 into 7 into 13. If you observe, prime factorization of denominator is not in the form of 2 to the power of n into 5 to the power of m. There exist another numbers 7 and 30. That's why this is not terminating. This is non-terminating repeating decimal. This is non-terminating repeating decimal. Did you understand, children? Fourth problem. Here also we have to write the prime factorization of 1600. Okay, we got 2. 2 8s 16, 2 zeros 0 again. 2 4s 8, 2 zeros 0 again. 2 2s 4 again. 2 1s 2, 2 zeros 0 again. 2 5s 10, 2 zeros again. 2 2s 4, 2 5s 10, 5 5s 25, 5 1s 5. So prime factorization of 1600 is equals to 1 2 3 4 5 6. 2 to the power of 6 into 5 square. So if you observe, prime factorization of denominator is in the form of 2 to the power of n into 5 to the power of m. That's why this is terminating decimal. Go for fifth problem. Here also you have to write the prime factorization of denominator. You have to recall table. This number is not divisible by 2, not divisible by 3. This is divisible by 7. 7 4s 28, 7 9s 63. Again recall table. 7 7s 49, 7 1s 7. So prime factorization of 343 is equals to 7 cube. This is equals to 29 by 77. 7 cube. So if you observe, denominator of this problem is not in the form of 2 to the power of n into 5 to the power of m. That's why this is non-terminating. This is non-terminating repeating. So for next problem, if you observe denominator of this one in the form of 2 to the power of m into 5 to the power of m, that's why this is terminating. Okay, go for this problem. If you observe denominator, this is not in the form of 2 to the power of m into 5 to the power of m. There exists another number 7 also. That's why this is non-terminating repeating. Okay, did you understand, children? Two remaining problems in exercise 1.3 as homework. Exercise 1.4. First problem. Prove that the following are irrational. So before going to prove these problems, first of all you have to recall the definitions of rational and irrational. What is rational number? A number which is in the form of p by q are called rational number. A number which cannot be expressed in the form of p by q are called irrational numbers. Here, if you want to prove this problem, we are using contradictory method. First of all, we are assuming this is rational number. Let us assume 1 by root 2 is rational number or rational. So, if a number is rational number, that is in the form of a by b equals to a by b. If you transpose root 2 from LHS to RHS, root 2 becomes as multiple of a. So, 1 is equals to a root 2 by b. Okay. Again, if you transpose b from RHS to LHS, b becomes as multiple of 1. Okay. 1 into b is equals to a root 2. Again, if you transpose a from RHS to LHS, a becomes as divided by b by a is equals to a root 2. If you observe this statement, root 2 is irrational. Already we know. So, this is in the form of rational number. So, we can't make it equal. Root rational and irrational. That's why this assumption, this is wrong. That's why our proof is wrong. That's why our assumption also wrong. So, 1 by root 2 is irrational. Go for next problem. Here also we are using contradictory method. First of all, we are assuming root 3 plus root 5 is irrational. Okay, let us assume root 3 plus root 5 is rational number. So, what is the form of rational number? Rational a by b. So, root 3 plus root 5 is equals to a by b. A by b. If you transpose root 5 from LHS to RHS, plus root 5 becomes as minus root 5. Okay. Root 3 is equals to a by b minus root 5. Okay. Now we are squaring on both sides. Squaring on both sides. What you will get? Root 3 whole square is equals to a by b minus root 5 whole square. Whole square. Square root cancel. 3 is equals to a by b minus root 5 whole square. If you observe this is in the form of a minus b whole square. A minus b whole square is equals to a square plus b square minus 2ab. Based on this formula, we can write it as a square plus by b square plus root 5 whole square minus 2 into a by b into root 5. Square root cancel. Square root cancel. Okay. 3 is equals to a square by b square plus 5 minus 2a root 5 by b. If you transpose minus 2a root 5 by b to RHS, LHS, 3 to RHS, what will get? 2a root 5 by b is equals to a square by b square plus 5 minus 3. 5 minus 3. Then 2a root 5 by b is equals to a square plus b square. 5 minus 3 is equals to 2. Okay. 2a root 5 by b is equals to a square. Okay. If you observe the denominators of these two, there is b square. There is no denominator. So, LCM of b square and 1 is b square. So if you multiply first term a square by b square into b square cancel, get a square, plus second term 2 into b square is equals to 2b square. Here we are transposing 2a by b from LHS to RHS. 2a by b becomes as b by 2a. Okay. Root 5 is equals to a square plus 2b square by b square into 2a by b becomes as b by 2a. Okay. B cancel. What we will get? Root 5 is equals to a square plus 2b square by 2ab, where a comma b are integers. Okay, so if you already know that root 5 is irrational, this is in the form of rational. We can't make these two are equal, so our assumption is wrong. So already we know root 5 is irrational. This is rational. These are not equal. That's why root 3 plus root 5 is irrational. This is our proof. This is our next problem. 3 plus root 2 root 5. Here we have to prove 3 plus 2 root 5 is irrational. Okay, we are using contradictory method. So for that we are assuming this is rational number. Let us assume 3 plus 2 root 5 is rational. Okay, rational, what is rational number? A number which is in the form of a by b is called rational number. That's why 3 plus 2 root 5 is equals to a by b. Okay, if you transpose plus 3 from LHS to RHS, plus 3 becomes as minus 3. Okay. 2 root 5 is equals to a by b minus 3. Okay. 2 root 5 is equals to, if you observe, denominators of these two terms are different. Here, if there is no denominator, we can keep it as 1. LCM of b and 1 is 1. Okay. LCM of b and 1 is b. Okay. After that, we have to multiply each term with LCM. Okay. What is first term? A by b. Okay, a by b into b. Cancel. b cancel. What is remaining? A minus. What is the second term? 3. We have to multiply the second term also with LCM. 3 into b, 3b. Okay, so if you transpose 2 from LHS to RHS, 2 becomes as divided by, okay, a minus bb by 2b. Okay, if you observe, this is a rational number, this is in the form of b by q, means this is rational number. These two are not equal. These two are not equal. That's why our assumption is wrong. Our assumption is wrong. Okay, root 5 is irrational number. Okay, so 3 plus 2 root 5 is irrational number. Okay, did you understand? So this is second problem in exercise 1.4. Prove that root p plus root q is irrational where p, q are primes. Already you know what is prime number? A number which is having only two factors, one and itself, called prime number. Okay, here we have to prove root p plus root q is irrational. For that we are using contradictory method. So we are assuming, first of all we are assuming root p plus root q is rational. Let us assume root p plus root q is rational. What is rational? A number which is in the form of p by q. Okay, root p plus root q is equals to a by b. Okay, if you transpose plus q from LHS to RHS, plus q becomes as minus q. Okay, root p is equals to a by b minus root q. Here, squaring on both sides. Squaring on both sides. What we will get? Root p whole square is equals to a by b minus root q whole square. Square root cancel. P is equals to, if you observe this one, this is in the form of a minus b whole square. A minus b whole square is equals to a square plus b square minus 2ab. Based on that, we can write it as a by b whole square plus root q whole square minus 2a by b root q. A square plus b square plus minus 2ab. Okay, square root cancel. P is equals to a square by b square is equal plus q minus 2a root q by b. Okay, if you transpose minus 2a root q by b to LHS plus q from LHS to RHS, what we will get? 2a root q by b is equals to a square by b square plus q minus b. Okay, here 2a root q by b is equals to, if you take p as LCM, there is no denominators. We have these two terms. If there is no denominator, we have to assume 1 is denominator. LCM of b square 1, 1 will get b square only. So we have to keep here b square as LCM. Later, you have to multiply each term with LCM. A square by b square into b square, b square, b square cancel. We will write here a square. What is our second term? Q. Q into b square, q b square minus p b square. After that, we have to transpose 2a by b from LHS